right? And we agree that when it comes to matrices, we can be able to convert a set of linear equations into a matrix form, right? Or vice versa. So that's what we're looking at. So an example here is that given this n equations with n unknowns, where the equations are equation 1, a11 x1 plus a12 x2, all the way to a1n xn to be equal to b1. The b1 basically becomes the unknown. And then we have the variables x1, x2, all the way to some xn. Now, the xi's are the unknowns, I'm sorry. And then the bi's are the various constants for each of the respective linear set of equation. So our main thing is that we want to be able to see how we can use matrices to express this set of linear equations and see how we can easily be able to compute them. So that's a big task. So we know for sure that we can be able to have this linear set of equations expressed as a times x to be equal to b, where the a is the coefficient matrix, and then the x is the unknown variables, and then the b is the constant, which is known. So at this situation, we can have the coefficient matrix a to be written as a11, a12 to a1n. Then we can have a21, a22, all the way to a2n. Then all the way coming down to an1, an2. I'm sorry, this is supposed to be an2, this one. Okay, so I'll correct it. It's not supposed to be ann. And then this is let's see what I can correct that shortly. Oh, sorry. All right, so I don't have the math type on this math book, but let's go ahead. So this is supposed to be an2, not an1, okay? What you can see here. And then we have all the way to ann, and then the x, which is the set of unknowns, become x1, x2, x3, all the way to xn. And then the b, which is the constant known values, become b1, b2, b3, all the way to some bn. So the dimensions can easily be identified as a, which is a square matrix, n times n. In other words, n rows, n columns. And then x also becomes n rows, one column. You can see row 1, row 2, row 3, all the way to the nth row, and then one column. And the same applies to the b, which is also n rows by one column. So at this situation, the number of unknowns is equal to the number of equations, which is the n number of equations. So at this situation, we can easily go ahead with regard to the ax to be equal to b. Because we are looking for the unknown variable x, we need to be able to make x the subject in that equation, ax equals to b, this one, right? Ax equals to b. So the x has to be made the subject so that we can easily be able to find the a. So how do we do it? We already know from some of the rules that the inverse of a multiplied by the matrix a itself will give us the identity or the unit matrix. So at this situation, the whole of this can be the identity matrix, this part. So this whole thing can give you the identity matrix I, right? Which is a set of ones. Then whatever I do to the left-hand side, I should also do the same to the right-hand side. So if I'm multiplying the left-hand side by the inverse of A, I should also multiply the right-hand side by the inverse of A. So that this situation, the whole of this goes away, and I'll be left with x to be equal to inverse of A times the B. Now, if I check so well here, I know that this A inverse will also have a dimension of n by n. And lastly, I can also have B, which I know from beginning having dimension n by 1. So if that is the case, the inner will agree And that should lead me to get x to be n by 1. And then I'm good to go. So if you switch it and you make it b times the inverse of a, it will not work because the inner dimensions will not agree. So always don't forget that it's supposed to be the inverse of a times the matrix b for you to be able to have x to have dimension of n times 1, n rows, 1 column. And we're good on that. Okay, so that's what I was mentioning, the inverse of a times a to be equal to I. So if the inverse of the coefficient matrix, right? The coefficient matrix is the A, this one is basically your A, your matrix A. Is found, then the unknowns X will be determined easily. So we need to be able to know how we can get the inverse of A, which the last time we met, we looked at it. To find the inverse of A, you need to first check the determinant. If the determinant of the matrix is not, then the inverse exists. So for you to find the inverse of any coefficient matrix, the main thing is that you need to be able to find out if the inverse of the matrix is not equal to 0. If it's equal to 0, then the inverse does not exist. Why? Because the inverse of any matrix A is the same as 1 over the determinant times the adjoint of A. So if the determinant is 0, it's going to be 1 over 0, and 1 over 0 is undefined. So that nullifies the inverse to exist. Now, to find the adjoint of A, we know for sure that the adjoint of A basically is you dealing with you having the transpose of the cofactors of A. And the transpose of the cofactors of A means that you need to find the cofactors of A. And how do you get the cofactors of A? You get the cofactors of A by adding plus and minus to the minus of A. And how do you get a minus of A? The last time we met, we were able to look at how you get a minus of A by finding the individual subdeterminants of the matrix. And that gives you the individual minus of A. Okay, so that is ideal situation what we looked at the last week. So I'm sure we're pretty okay with it. So let's look at this example, right? So we have this first set of equation 1. And then we have the next one, equation 2. Then we have the next one, equation 3. So there's a 3 set of equations that we expected to also look at. So our main thing is we need to be able to get a coefficient matrix A. And how do we do that? Looking at the equation is easy, right? You should be able to know that for this set of equation, I can be able to have my 3, my minus 1, 1. How? The coefficient of x1 is 3. The coefficient of x2 is minus 1. The coefficient of x3 is also 1. And then at the end, I can be able to also have my b right here, which is a constant associated with the first equation. So that becomes 2 here. Then when I come to the second equation, I pick the coefficients, right? So the coefficient of the second equation, x1 is 2. So that comes here. X2 is 1. There's no x3, so you can't get a coefficient of x3. So I represent that with a 0. Because 0 times x3 will always give me 0. Then I have the 1, which actually becomes a b2. So I bring it out here. Then I go to equation 3, pick the coefficient of the unknown variables x1. So that's here, 1. Coefficient of x2 is 2. Coefficient of x3 is minus 1. Then the b3 here becomes 3. So at the end, I can have my coefficient matrix this. I can have my b. Then I can also have my set x. That's going to do with my x1, x2, x3, and I'm good. So once I have this, I don't have any issue. So in this case, I can be able to have my x to be equal to first finding the inverse of A and then multiply it by the B. And this, the calculator can easily do it for you, right? So the last time we met, we agreed that if you have anything at all, you should bring your calculators and we should be able to look at it. I hope you bring your calculators. Someone has a question, said.
Yes, sir, we brought a calculator.
Okay, so please, assuming that we have A equals to rows, I don't understand, columns, then A inverse B rows. Sorry, the one, Justice, I'm not really getting what you're trying to say. So if you can, I can give it a chance to unmute and talk about it. All right, but let's move on. I'll maybe Justice atmosphere is not okay. So when it's free, you can raise your hand. So we good here, right? Now, let's see how we can easily be able to go ahead with it. Unfortunately, I don't even have my calculator with me, but let me see whether I can still remember some of the steps. So for the calculator, what are the versions you're having? Let me see the models you're having.
I have a FX, that's the ES plus.
Sorry, come again.
The second edition, scientific calculator.
Calculator
FX, the ES
What do
plus.
you have? ESFS, what do you have?
FS.
FS what?
99,
There's a number on it.
991 ES plus. Yes, FX 991 ES plus.
Okay, FS 991 ES. And which one again is anyone having? Okay, so that is okay. So at this situation, we can use that. But before that, Justice, I see your hand up. Please go ahead.
The question I was asking is that let's assume we have a matrix A and it's having A rows and B columns. So when you find the inverse, will you have B columns and A rows, B rows and A columns?
Please repeat that again. Sorry.
Assuming you have a matrix A and that matrix is having A rows and B columns. When you find the inverse of the matrix A, will you have B rows and A columns?
Oh, okay. So you mean that when you have a matrix that has, let's say, A rows and B columns, right? Remember, you can only find the inverse of a matrix if it's a square matrix.
Mm-hmm.
So the number of rows should be the same as the number of columns. That's the first thing.
Okay.
So at this situation, if the matrix is a 3 by 3, the inverse will also be 3 by 3. If the matrix is a 2 by 2, the inverse will also be a 2 by 2. If the matrix is a 4 by 4, the inverse will be a 4 by 4. Justice, you good on that?
Okay, thank you, sir. Yes, please. Thank you.
So let's move on. I'll get back to you on the calculator shortly. Right. So for now, we assume we can easily be able to input this in the calculator. I'll get back to you. Right. Now, if you're able to do that, the calculator can easily be able to get an inverse for us. And at the end, we multiply with a B, and that gives us our X. And we don't have any issue with anyone. Okay. So that is the main thing we need to do. So once you do that, you should be able to have the 3 by 3 matrix to be the following, and then you multiply it by the B. Even that one, the calculator can still do that for you as well. They can have this. Okay. Now, the values for the unknowns should be checked by substituting back into the initial equation. Once we have it, obviously we are expected to get x1, x2, x3, and then we can slot it back into the equation, and that gives us the actual constant b1, b2, b3. Okay, so that's what we got to the last time. Okay, and then I ask you to get your calculators, then we take it up from there. Okay, so any question before? Let me see whether I can get some calculator. All right, so apart from the FX 991EX, what else do you have? Which different version of calculator is someone having? Okay, so this is it. So the FX 991, the Casio FX 991 ES Plus, right? The scientific calculator, it really helps. So let's see probably how I can be able to walk you through. So when you have your calculator, right? Imagine we are going to input these values. Please, the one writing on my screen, can you stop that? Okay. All right. So imagine I want to be able to enter the 3, -1, 1, 2, 1, 0, 1, 2, -1. Let me see what I calculate. I don't have a calculator with me, but I'm trying to see whether I can remember the steps. Okay. So once you have your calculator, at this situation, the scientific calculator, the Casio FX 991 ES Plus, right? You see where the mode is, right? You can click on the mode, and at this situation, you should be able to have access to matrix. Okay, so once you click on the matrix, you'll be provided with matrix A, matrix B, matrix C, right? For you to be able to enter the values inside. So if you choose any of the matrices, let's say matrix A, it will ask you to specify the dimension. Now, since the matrix you are seeing currently is a 3x3 matrix, you should be able to specify 3x3 matrix. Then you can easily be able to enter the values into the specified 3x3. And the values is 3, -1, 1, 2, 1, 0, 1, 2, -1. Okay. Once you do that, then you are done with matrix A. Now you can come back again and also enter matrix B. Matrix B in this case, the 2, 1, 3. So you have matrix A, which is capturing the coefficient matrix 3, -1, 1, 2, 1, 0, all the way to 1, 2, -1, 3x3. Then you also do the same thing for matrix B. And matrix B is expected to have a dimension of a 3x1. So once I specify a 3x1, it will give me the option to specify the elements 2. Once I enter 2, I press the enter or the equal to, right? Then it gives me to the next one. So I can go to 1, then I can go to 3, then I'm done. Okay, now when I'm finished, when I'm done with this thing, I can easily cancel it, right? When I say cancel, you can just come to the AC, which has the off, the inclusive. I'm not saying off the calculator. I just press the AC to clear the screen. Now, when you clear the screen, you can see that on top of the 4, you see some matrix over there. On top of the 4, number 4, you can see matrix there. Now, to access that, depending on the color, and probably if it is expected to be, I'm sure orange, you can use the shift and then press the 4. If it is expected to be a different color, right, which I know, whatever you're having will deal with orange color. So please, you press the shift and press the 4. That should populate you with matrix A, matrix B, matrix C. Now, so what do we want to do? We just want to be able to find the inverse of matrix A and then multiply it by matrix B. So I can easily pick matrix A, which will have a number of 1. And once I pick matrix A for the number 1, or number 1 for matrix A, for inverse, if you check your calculator underneath the mode or setup, you see x raised to the power -1 there, right? X raised to the power -1, that is for your inverse. So once I pick matrix A, that is shift 4, I have to press that x exponent -1, which is underneath the mode stroke setup. And that is expected to give me the inverse of A. Then I can just go to times, right? The normal multiplication, because you are multiplying the inverse of A by B. So if I take my times, right, underneath the del, DEL, I can now go back again to now pick matrix B. Matrix B is now containing the B values 2, 1, 3. So simply put, if I have my matrix A, I have my x raised to the power -1, I have my times, I come back again to come and pick the shift and go to 4. And the shift going to 4 will help me to be able to have a pool of matrix A, matrix B, matrix C. Now my interest is matrix B. So I'll now pick matrix B. number 2. Then I can press equal to. And once I press the equal to, it's expected to give me the results I am seeing here. Right? 2 negative 37. So basically, that is how you can easily use the calculator to do your matrix multiplication. Now, the same way, if I also want to, I can't see what Sarah is saying. You don't need to see. This is online class. I'm assuming there is a virtual calculator I'm having, so I'm not showing it. Right? Some of you are saying I can't see. I'm not showing it. All I'm saying is you should have your calculators with you, and then I'm just demonstrating probably how you can use it to do your matrix multiplication, matrix inverse, and other stuffs. Okay. Someone said I should solve the example manually. All right, why can't it be solved manually? They can be solved, but I don't have that time to solve it because at the end, it's going to take more time. Just to recap, I'm told that this is officially my last meeting with you guys. So I just saw that thing from our platform. This is your 8th week, right?
Yes, sir.
Yes.
Okay, but notwithstanding, officially I'm supposed to end today. I only meet you for revision, but I will still meet you guys next week. When did I see you right? When did I see you right there? Is it next week? Guys, can you hear me?
Yes.
Yeah, we can hear you.
And did I agree with you the time you right the I?
No, I don't think so.
All
No,
right, so
sir.
let's go ahead. Let me get to some place, then I'll be able to discuss that. So, but next week I'll still meet you guys. Okay. So please, for you to find this manually, the main thing is to have your inverse, A inverse, to be equal to 1 over your determinant. So let me use this determinant. Determinant of A times. Please mute yourself. Please mute yourself. Adjoint of A. Amma, please mute those who are disturbing. That's why I made the co-host. Adjoint of A. So then how do you find the adjoint of A? This adjoint of A is by finding the cofactors transpose. So this guy, right? Let me just bring the arrow down here. This is the same as cofactors. Now, you only need this when you are dealing with a 4x4 matrix. It is a 3x3, as I mentioned. You don't need to waste your time to come and do this manually. Okay.
Provided that you give us.
Yeah.
Please, in the exam, are we allowed to use our calculators?
Are you allowed to do what?
Are we allowed to use our calculators?
Of course. You have to use your calculators. If not, why would I waste my time to teach you how to use the calculator to solve this? Please, you understand? So that's the cofactors of A transpose. Now, how do you get the cofactors of A transpose? This one is basically you dealing with the minus, right? So there's a way you have to add a plus and minus to the minus of A. And basically that is what we refer to as the cofactors. So, and how do you get a minus of A? That's where the main thing starts. So to find the minus of A, you just pick this value 3, right? You cross. Last I met you, I'll explain this thing to you. Then you find the determinant of 1, 0, 2, -1. And that should give you the first minor of A. You can put it here, M1. Right? Then when you are done, you go ahead to also find the second minor of A. And how do I find the second minor of A? The second minor of A is as follows. I cross here, I cross there. Then I find the determinant of 2, 0, 1, -1. And that should give me the next minor, M, 1, 2. Good. Then I do the same for the next one. Okay. Here. Then I can easily find the determinant here. Then I can also put it here. Then I come back here. So here I have to clean this. So when I'm at 2, I can easily find the minor here. And that's supposed to give me M21. I bring it down here. So remember, the minus is going to give me some form of a 3 by 3 matrix. Can you see that? Then we have M21 here. Then I need to go and get M23, which is going to be under 1. So in that case, I can easily clean this. Okay. And then I can easily have this cross. And I need to get a determinant of 3, 1, 1, -1. And that should give me M21 here. Then I can go ahead and then do same for the next one. And that's expected to give me M23, right? So I cross here, then I have this. So that's going to give me 3, -1, 1, 2. And that should give me M31 here. Then I move on again to try my hands on the last set. So what do? I need to just come and cross. So in here, I can cross this and cross that. And that should give me -1, 1, 1, 0. And that should give my M31 down here. Can you see that? Then I can easily go ahead and do the last two. And the last two is the one on top of the 2. Here. So that's going to give me the determinant of 3, 1, 2, 0, which you can easily do. And that should give me my M32. And then lastly, I need to get my M33. So I clean this. And that's that. So I'm going to have determinant of 3, -1, 2, 1. And that should be my M33 here. Now, when I'm done with the minus, all I need to do to get a focal factors is to add the plus, the minus, the plus. Here will be minus, plus, minus, and this will be plus, minus, plus. It's just a matter of multiplying through by the -1 and then +1 sequentially. So you start with the first element M11, you multiply with +1, you move on to the next element M12, sequentially multiply by what? -1, then the M13 becomes +1. Then when I come down all the way to M21, that becomes a negative, and then the M22 becomes positive, and then the M23 becomes negative. Then I can come down to M31, that will become positive, M32, that will become negative, and then M33, that will become positive. Then I'm done. So once I'm able to get the cofactors of A, all I need to do is to transpose it. Transpose means that the rows become the columns become rows. And that gives me what we refer to as the adjoint or the adjugate of A. So the transpose of the cofactors give you the adjugate of A. And when I have the adjugate of A, all I need to do is I find the determinant of A, which by now each and every one of you should know. So the same way we're going by this. So this will be 3 times the determinant here. This will be minus, so it will be minus, and that should be plus 1 times the determinant of 2101 plus 1 times the determinant of 2112. And that will give us the denominator here. And I'm good to go. So the main focus here when you're dealing with the inverse of a matrix manually is to spend more time on the determinant. Okay, then we are good to go. So if there's no question, I think we can end the session on matrices and start another thing else. Okay. Question? Guys, please, can you hear me?
The line is breaking, sir.
My line is breaking.
Yes, sir.
Hey, are you sure? Please, what about now?
I think it's okay now.
So does it mean all that I said in the matrix, you didn't get it? Was I breaking when I was teaching the matrices?
No, sir. No, sir.
Okay, so everyone is okay.
Yes, sir.
Good. So please, we can move on to sessions 8 and 9 put together, right? And that has to do with the recursion and relation. Any question before we move on?
About maybe people who choose to
Okay, so if there's no question, we move on, right? And please, if I'm breaking, let me know, right? So that I can check my network. So for sessions 8 and 9, as I mentioned, we're looking at recursion and relation. Please stop writing my screen, Jefferson. Okay, so at the end, we want to be able to define functions recursively, define bases and the recursive steps. Andy, please stop writing my screen. Understand the properties of relation, and then understand equivalence relation. So the key topics we'll be looking at has to do with the following. So before we start, Jefferson Quay, stop writing on my screen. So the recommended text for you to read will deal with the chapters 5 and then 9 respectively. Okay. So I'm going to stop sharing and then reshare again so that those who are doing that will stop. Okay. Okay. So let's start. Recursion. Recursion basically refers to the process of defining an object in terms of itself, right? So when you talk of recursion, you want to be able to keep on calling an object a number of times until a particular set of property is met or a rule is met or until convergence. And that's what we refer to as what recursion. So the process of calling an object a number of times or defining an object a number of times is what we refer to as recursion. We make use of it in district structures like functions, set sequences, etc. So let's look at a simple example. We want to consider the sequence of powers of 2. Now, the powers of 2 basically will be dealing with 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, all the way to some 2 to the power infinity. So the terms of this sequence can be specified using the formula A of n to be equal to 2 raised to the power n, where this 2 raised to the power n is for n equals to 0, 1, 2, 3, all the way to infinity. Please hold on. So let's continue. This sequence can be defined recursively. In terms of defining any function recursively, we need to have 2 main steps. The first one is what we call the basis step. The next one is what we call the recursive step. Okay, so when we talk of the basis step, basically we are looking at it from this angle, the initial step or the fundamental step. And normally we assume 0. Okay, so what do we do? So the sequence can be defined recursively as A of 0 to be equal to 1. Why? Because the first power of 2 can be 2 to the power 0, which is the same as what? 1. Followed by 2 to the power 1, which is the same as 2. Followed by 2 to the power 2, which is the same as 4. 2 to the power 3, which is the same as 8. 2 to the power 4, which is the same as 16. All the way to positive infinity. So the basic step now becomes A of 0 to be equal to 2 to the power 0, which is the same as what? 1. Now let's look at the recursive step. So for the recursive step, we know that once I am done with A of 0, I need to increment it to get the A of 1. Then at A of 1, I need to increment it to get A of 2. At A of 2, I need to increment it to get A of 3. But in terms of recursion, we are going to be calling the previous step in the next submission. So if I'm at A of 0 and I move on to A of 1, I need input from A of 0. If I'm at A of 2, I need input from A of 1. If I'm at A of 3, I need input from A of 2. All the way till I'm done. So A of 0, which is the same as 2 to the power 0 or 1, but I come to A of n plus 1, I'm actually going to have this definition, 2 times A of n. Okay. 2 times A of n, where my n here will denote 0, 1, 2, 3 to infinity. So how do I do it? If my n is 0, this is expected to be A of 0 plus 1, which is the same as A of 1. Then when I come here, remember my n is 0. That is actually going to give me 2 times A of 0. Now 2 times A of 0 means that the A of 0, I already know it from the basic step. Remember the previous step, which is what? A of 0 is 1. So at this situation, I'm going to have 2 times 1. And 2 times 1 is going to give us 2. So meaning that I can get my A of, right here. I can easily get my A of 1 to be 2. And the next one I have to do is increment the n by 1 again. So I started with n is 0. The next one I need to go is n is what? It's 1. If n is 1, I'm going to have A of 1 plus 1, which is going to give me A of 2. So that's going to give me A of 2 to be equal to 2 times A of 2. Sorry, 2 times A of 1, I'm sorry, because n is 1, I'm sorry. So this one will be 2 times A of 1. Now, because we are dealing with 2 times A of 1, we already know A of 1 from the previous iteration to be 2. So that's going to give me 2 times 2. Then that will give me what? 4. Are you with me? Then I can now move on to do with when n is equal to 2. If n is equal to 2, I get here. And that's going to give me a of 2 plus 1, which will give me a of 3. Now, when I'm at a of 3, I can easily go to the right-hand side. And that's going to give me a of 2 times a of 2, because n is 2, this one. So that's going to give me 2 times a of 2. And what is a of 2? A of 2 here is 4. So that's going to give me 2 times 4, and that's going to give me 8. And I can do that to positive infinity, then I'm done. So that is it for the recursive definition of a particular set of equation. Now, recursive definition is also known as inductive definition. So let's take note of that. So this one, I just explained it, right? So we can have a function with a set of positive integers as its domain can be defined recursively. So we have the basic step, specify the value of the function at 0, which I mentioned. And then we can have the recursive step, give a rule for finding its value at an integer from its values at smaller integers. Okay, then we are good to go. So let's look at another example and see whether the understanding will come. Give a recursive definition of a raised to the power n, where a is a non-zero number and n is a non-negative integer. So basically that's it. So at the end, what do we need? We need to be able to know that if you are looking at n being a negative integer, then negative integers is actually dealing with integers that does not include integers, negative integers. So I can list them as what? 0, I can have 1, I can have 2, all the way to positive infinity. So basically, non-negative integers will deal with the 0 plus positive integers. In other words, when we pick the set of integers, we are excluding only negative values from it. So that's going to give me negative infinity all the way coming down to -4, -3, -2, -1. That's it. So non-negative integers, 0 is included, plus the set of positive integers. So with this, we're good to go. All we need to do is that we can easily be able to come here when n is what? 0. I'm going to have a of 1. And a of 1 to be equal to this a times a. N is, we already know n is what? N is 0. So that's going to give us a times a raised to the power 0. And a raised to the power 0, we already know here to be what? To be 1. So at this situation, a of 1 is going to give us what? A. Because it's going to give us a times a raised to the power 0. And a raised to the power 0 is 1. So at the end, a of 1 will give me what? A. Then I can easily move on to deal with when n is 1. So if n is 1, that's going to give me a raised to the power 1 plus 1, which is going to give me a raised to the power 2. And a raised to the power 2 is the same as a times a raised to the power what? 1. And I already know a raised to the power 1 from the previous example to be what? To be 1. Sorry, to be a. So if it is a raised to the power 1 here, at this situation, we have a times that a, and that's going to give me a squared. Then I can move on and on till I exhaust it. So that's how we define functions recursively. Any question before we move on? Please, can you hear me?
Yes, sir. Yes, sir, we can hear you.
Okay, so I believe that everything is going as expected. Now, let's look at this example. And this one, I want you to give it a try, your own, right? Consider the function f defined recursively as follows. F of 0 equals to 3, f of n plus 1 to be equal to 2 f of n plus 3, The main thing is to find f of 1, f of 2, f of 3, and f of 4. Can you please try your hands on it?
Yes, sir.
So please use some 3 minutes to try your hands on this, then we continue. Please, are you done?
We tried our hands on.
Should we look at it together, or some of you are still solving it?
I have an answer, but I don't know if it's right.
Okay.
But F1 I got 9.
Okay. How did you get
F2
F1 to be
21.
9? How did you get
I put a value.
Please go ahead.
I replaced the value, the Fn with the value of the F0.
You place Fn with a value of 0. In other words, you made n to be 0. Is that not it?
F0. Yes, well, the 3.
So when you are saying that you started with n to be 0, is that not
Yes.
okay? Good. So if n is 0, I'm going to have f of 0 plus 1. That'll give my f of 1 to be equal to 2f of what? 0 plus 3. And because we already know f of 0 from the previous iteration, in other words, from here, I'm easily going to have 2 times 3 plus 3. 2 times 3 already know is 6, plus 3 is going to be 9, okay? So that's what happens. We get to the 9. Now, once you're able to do this, it's easy to be able to get the F2. F2, you need to be able to make n to be equal to 1. So if n is equal to 1, that is actually going to give you f of 1 plus 1. That's giving us f of 2 to be equal to 2f of 1 plus 3. So at the end, we are going to have this f of 2 to be equal to 2f1 plus 3 to be equal to 2 times 9 plus 3. That'll give us 21. And I'm sure that's what some of you had. Did you all get 21?
Yes, sir.
Good. So we continue, and then we're able to get F3, F4, respectively, to be 45 and 93.
Exactly. Exactly.
That's what we are.
Please, any question on this? Who doesn't understand it?
Please, I don't too.
Please, I don't understand.
You understand? Okay. So let's look at it quickly. So what we are saying is, you have been given f of 0 to be 3. You have been given f of n plus 1 to be equal to 2f of n plus 3. Okay. And then the question is asking you to find f of 1. Now, to find f of 1, you need to make a substitution for n. If you start with a substitution n equals to 1, it will not work. Because when n is equal to 1, this will be f of 1 plus 1, which will give us f of 2, and that is here. Now for f of 2, even when they come here, it's going to be 2 times f of 1, because it said n is 1. 2 times f of 1 plus 3. And you don't know f of 1 in the equation. So there's no way you can be able to go by it in that way. So rather, you need to start with n equals to 0. And when you start with n is equal to 0, it's going to be f of 0 plus 1. That should give you f of 1. To be equal to 2 times f of what? 0 plus 3. And for f of 0, we already know it here. To be 3.
Can you write 10, please?
Oh, Sean, how can I write for you? Okay, so let's see. When n, so for, I'll just do 1, right? Then we see whether we can do that. So for f of 1, please mute yourself, okay? We need to be able to make the substitution n is equal to 0. That's the main thing. So if we make the substitution n is equal to 0, at the end, we come to this equation, this one. The one I'm highlighting, okay? Now, when I come there, because n is equal to 0, I'm going to have f of 0, because n is 0, plus 1. To be equal to 2 times f of n. And that n, we already know is what is 0. Plus 3. Are we okay? Now, 0 plus 1 give me f of 1. So once I get f of 1, I am good to go. Why? Because the question is asking me to first find f of 1. Are you with me? So this is my f of 1, the question is asking me to find. So now what do I have here? I have 2 times f of 0. But there's f of 0 here. Can you see? F of 0 is 3. So I can now have 2 times my f of 0, which is 3, plus my 3. If I want, I don't have any issue, I can just put it in the bracket, right? And that's going to give me 2 times 3, which is what? 6. 6 plus 3 will give me 9. Okay, sorry. Can you see that? So this is actually going to give me the 9 I can see. So use the same approach to solve for f of 2. So to get f of 2, you need to make n is equal to 1. So that this part will be f of 1 plus 1. That'll give you f of 2 to be equal to 2f of 1 plus 3. Because I'm making it to be equal to what? To be equal to 1.
Sir,
Yes.
please, I want to know if you are supposed to use 0 in every situation, like 0 to begin
No.
the solution in every situation, or
No.
you are supposed to use what is given to you in the recursion first.
So the answer to that question is no. It's not always the case you have to start with 0.
Okay.
There's an instant you might have to even start with -1. So depending on how the logic works. But this one, if you start with -1, it will not work. Why? We're going to have n to be equal to -1. That's going to be f going into -1 plus 1. Right? And that's going to give you -1 plus 1 give you 0, which is okay here. Equal to 2 times f of -1 plus 3. So that's, I'm supposed to look for f of -1. And I don't know f of -1. Rather, I was given f of 0 to be 3. So it depends
Okay.
on what you are giving. That will
Okay.
prompt you to know what to use. Okay,
Okay. Thank you very much.
you're welcome. All right, so I think with this, we're good. I can easily be able to move on, right? Okay, so because of
Sir,
time,
please
let me show us what-
let's solve the 2 f of 2. Maybe that will be okay with
that will
me.
bring more
Or
understanding.
yes, please.
Okay, all right, so I'll do that. So for f of 2, I'm going to have n to be equal to 1, right? So that I'm going to have here, still coming back to this equation, I'm going to have f of n is what? 1. So I'm going to have 1 plus 1. Can you see that? To be equal to 2 times f of 1. Because n is 1 plus 3. So that's actually going to give me f of 2, because 1 plus 1 will give me f of 2 here. Now f of 2 here will now be equal to 2 times f of 1. But I know f of 1 from here. See, f of 1 is 9. So that's actually going to give me 2 times what? 9. Can you see that? Because I already know f of 1 from the previous example. Then plus my 3. So in here, 2 times 9, we know is what? 18. 18 plus 3, that's expected to give us 21. That should give me 21. Then I'm done. So I hope the one who asked the question, you're okay with it.
Thank you very
F of
much.
2.
Thank you very much.
Great. So you can do the same for f of 3, f of 4, and go
Okay.
downwards, right?
All right.
So
Thank
now
you.
we can move. You're welcome. So this example too is same. I'm not going to waste time on this. Let me explain the Fibonacci for you, right? So this one, and what you read on it. Now, for Fibonacci sequence, what we are trying to say is that any sequence that either start with a 0 or 1, the next number is expected to be 1. And then the next number will be the sum of the previous two numbers. That is how we define a Fibonacci number sequence. So a Fibonacci number sequence is any sequence of numbers which begins with either a 0 or a 1. So either I begin with a 0 or I am beginning with a 1. The next number is mandatory a 1. So if I begin with a 0, the next number will be 1. If I begin with a 1, the next number will be 1. And then the next number is where the Fibonacci sequence comes in. It's going to be the sum of the two numbers, the previous two numbers. So 0 plus 1 will give me 1. Are you with me? So here, the sum will be 1 plus 1. Will give me what? 1. 2, sorry. Then I go ahead to pick the next number. This will be 1 plus 2. That'll give me 3. To pick the next number, it will be 2 plus 3. That'll give me what? 5. To pick the next number, it will be 3 plus 5. That'll give me 8. To get the next number, it will be 5 plus 8. That should give me 13. All the way to infinity. Now let's come here. Assuming I started with a 0, the next number is 1. The next number is the sum of the previous two numbers, 0 and 1. So that gives me this one. Then the next number will be 1 plus 1. That'll give me 2. The next number will be 1 plus 2. That'll give me 3. The next number will be 2 plus 3. That'll give me 5. The next number will be 3 plus 5. That should give me 8. And of course, the next number should be what? 5 plus 8. That should give me 13. If you want to continue, then it's going to be 8 plus 13. And that should give me 21. Of course, we can go ahead to deal with the others as well. It's going to be 13 plus 21. And then whatever number you get, you add it to the previous number. And that gives us a sequence of Fibonacci. So the recursive definition of a Fibonacci number sequence is the basic step will be f of 0 to be 0 or f of 1 to be 1. Basically that. That's the first thing. Down, the recursive step will be f of n to be equal to f of n minus 1 plus f of n minus 2. So simply put, what we are saying is that if I want to find the third number, in other words, n is 3, I need to be able to have the sum of the first and the second. If I want to find this number, I need to find the sum of the two. If I want to be able to get in this number, I need to be able to have the sum of this and that. So what this means is dealing with the sum of the previous two numbers. That's all. If you start with 0, it means I'm going to have f of 0 here, which is going to deal with this number, f of 1, which is going to deal with this number, f of 2, which is going to deal with this number, and so forth. So that's good, right? So we can define sets recursively based on the basis and then the recursive step. So let's look at some example. All positive multiples of 3 can be recursively defined as positive multiples of 3. We know that we can be able to have first the basis step to be 3 being as a member or an element of the set S. And then we can now go ahead to look at the recursive step, which is going to be probably X being a member of some S, and then Y also being a member of some S. Then at the end, we can easily be adding these two numbers and we're good to go. Alternatively, we can always be adding 3 to the X, assuming the X is the one keeping track of the number of increments of the multiples of 3, and then we are good to go, okay? For even numbers, we can easily also define it as follows. Remember, 0 can be the first even number you can think of, followed by 2, 4, 6, 8, all the way to positive infinity. So that also can be also as this, X being a member of S, then we can have X plus 2, which can also be element of S. Then at this situation, if you also have the set sigma star of all strings over the alphabet deals with A, B, C, D, all the way to Z. So that's a sigma. We can define it recursively as follows. So first, we can have an empty string, right? Whereby nothing is inside. And that becomes the basic step. And then the recursive step is going to deal with, assuming we start populating it with alphabetical values or alphabets, then that string is no longer empty. So it's going to have, if W is an element of sigma star, and sigma star deals with the set of all strings, okay? Then we can also have X being an alphabet from the set of alphabet sigma. Then at this situation, WX will be an element of the sigma star, which deals with the set of what? All strings. So basically that's it. So at the end, the basic step is empty. When they start putting values from the alphabet set into it, then they start gaining weight. Relationships between elements of two sets. So we can always find whether there is any correlation or relationship between a pair of sets we are looking at. Okay. So we can use a relationship to determine the pairs of cities that are linked by airline flights. That's one of the things we can think of in terms of application. We can find a variable order for different phases of a complicated project. So in any project we are working on, if the project is divided into components or modules, we can easily be able to use the relations to be able to know if I'm moving on to module B, what was the previous association it had with module A, and what is the association going to have with module C. Then move on with that. And producing a useful way to store information in computer databases. I can easily be able to have storage of all my values, those with relations. So let's see how the relation works. So some terminologies we need to understand. We need to understand the binary relation, and that's what we're going to focus on. So the set of ordered pairs represent the relationship between elements of two sets, right? Hence, we call it binary relations. So we have set A, which has some ordered elements on it, set B, which also has some other elements on it. Once we want to be able to find the level of correlation or association or relationship between them, then we can call it the binary relations. So a binary relation from a set A to a set B is a subset of all the Cartesian product of A and B, which you can see here. Okay. Which is denoted by R. So we came across a Cartesian product when we were dealing with sets. So that's something I really believe you already have it. Okay. So if they are related, we can use this notation, right? A, R, B to denote that A and B are related. Remember, A is from set A, this one, and then B is an element in set B. Okay. So we can easily be able to use A, R, B to denote that A and B are related. And remember, A and B are from the Cartesian product of A and B here. Now, we can also use A, B to also denote that they are related. Now, if they are not related, then this will cross. As you can see here, AB is not an element of the R. Or we can use A, R/B to denote that A and B are not related at all. Okay, so these are some terminologies we need to really be able to get a concept of. Now, when A and B are related, A is said to be related to B, right? Which you already know by what? By the relation R. Now, the relationships among elements of more than two sets, right? So assuming there is a Cartesian product of A, B, and C, we can be able to express this as what? N-ary relation. So if N is 3, you can say 3-ary, N is 4, N is 5, whatever value we are having. We use that, but we are going to focus on just the binary relations, okay? So let A be the set of students, B be the set of courses. The relation R that consists of the pairs A, B may represent that a student A is a student enrolled in a course B, right? This is straightforward. The same applies here to the airlines. We can have let A be the set of cities in US, B be the set of 50 states in the US. Then let B be the relation with ordered pairs such that an ordered pair AB belongs to R if a city A is in the set B. Okay, so those are things we can be able to grasp. Let's see, relations can be represented graphically, or you can also use a table. So this is the tabular representation of the relation, and this is a graphical representation of the relation. Now, let A be equal to 0, 1, 2, and then B be equal to A, comma B. Right? So we can easily find the Cartesian product of A and B. We already know, right? So Cartesian product of A and B, we can have A, comma 0A, 0B, 1A, 1B, 2A, 2B. And that will be the Cartesian product of A and B. A cross B. Remember, we looked at the drawing set. But if you're looking at relation, right now, you see the relation as a form of association. So it doesn't mean that all elements in A should be related to the elements of B. So that R will define those that are related. Even in your current class you are in now, those who are having this session, I will not be able to stand here and say that every lady knows every gentleman in the class. It's not true. So some ladies will know some gentlemen and vice versa. But if you want to find a Cartesian product, we assume that every lady will know every gentleman in the class. So what are possible combinations would be existing? But Cartesian product will pick a subset. Sorry, the binary relation will pick the subset of the product between A and B. Then we are good to go, right? So this defines a relation. This is a defined thing. So please don't ask me why. It's an example, right? So we are assuming that for this kind of relation, 0 from the set A is related to A from the set B, right? And then 0 from the set A is also related with small b from the set B. And then 1 from the set A is related to A from the set B. And then lastly, 2 from the set A is related to B from the set B. So that's it. That's the relation.
Hello, sir.
So yeah, we can say 0 is related to A. Yes, go ahead.
Please, why is 1 not related to B in the set
That's
B?
what I'm saying that. That's what I'm saying that it's an example, right?
Okay.
If it was a Cartesian product, then you have all the possible pair combination.
Okay.
But this is an example, okay?
Okay.
So
Okay.
let's take that rule.
All right.
Okay, so in here we can say that
Sir.
0 is related to A,
Hello,
but
sir.
1 is not related to B. Yes.
Yeah, so with this very relation you actually did here, can I actually relate it to just like the mapping you taught us earlier, so that maybe A is a student in 0, like stuff like that. There is a connection between it. A maps to 0, just like definited in the table here. Can the relationship be computed in that way?
Okay, we can do that. So in fact, we can even do it in a nice way. So the previous example, as you are mentioning, 0, 1, 2 probably can be the various. Let's assume these are the
number of
various courses
students.
or number of students, right?
In
Anyhow you
class
want to put
A
it.
and class B.
And this would be class A, class B.
Yes.
So at the end, we can say that 0, here, remember, 0 is actually a number here, right? So if 0 is in class A, right, we can say that the 0 basically will be a student, right?
Yes.
1 is also another student, 2 is another student. So 0 is in class A,
Yes.
right?
Yes.
And then here, that same 0, let's use the A and B to be the courses. That will actually make sense, right? So 0, who is a student, is enrolled in course A. That course A can be 105. And then we can also say that that same 0 is enrolled in course B. Course B can be start, right? The start course you guys are doing. Is it start 111?
Yes. Yes.
Okay, great. Then we can now come back here and say that 1 is only enrolled in one course, the course A,
105.
which is 105.
Yes.
So in here, 1 is not enrolled in start 111. And then when we come here, 2 is not enrolled in 105, but rather 2 is enrolled in the start course. That's 111. Okay?
Yes.
So if that is the case, we can use that same rule to be able to represent it graphically. So 0, 1, 2, then this is AB, then we can do our mappings. Okay? So 0 is related to A, you can see here. 0 is related to B, which you can see here. And then 1 is related to A, right? Which you can see here. And then 2 is related to B. So that is a graphical representation. Then for the tabular representation, we have A, B being the columns, 0, 1, and 2 being the respective rows. So if I have 0A, it is there. So I can indicate that with a cross. Then I can have 0B. It's also there. Then I can have 1A. Okay? Which is there. But I cannot have 1B. It's not part of it. So I leave it. Then I can have 2B. 2B is here. But I cannot have 2A. So that one is also left blank. Okay? So let's look at some properties when it comes to relations. The first property we're going to look at has to do with the reflexive property or reflexivity property, right? So the reflexive property basically deals with a particular element related to itself. So we can say that probably in this particular class of 105, you don't have any student who has any friend. So everyone wants to be independent on its own. When assignment is given, you want to learn on your own. You don't want to learn with anyone. So you're only related to yourself. So a relation R on the set A is called reflexive if A is related to itself in that given relation for every element A belonging to cap A, the set A. That means that an element A is always related to itself. It doesn't have any friend apart from itself. And there are people like that, okay? So they are only related to themselves, right? So we can even think about it from one particular siblings, right? The nuclear family, they're only related to them, so they don't want to go outside, okay? Let R be the relation on the set of all people consisting of pairs XY, where X and Y have the same mother and probably the same father. So the siblings I was mentioning, right? Then X can be related to itself for every person X. Now note that a relation R on the set A is called irreflexive if for every A belonging to cap A is not related to itself. That is, R is irreflexive if no element in A is related to itself. So once the relation is given, right? So for example, like this one, if I was having 0 is related to itself, 0, then we can have another type of reflexivity in there. So, but when I come here, I have considered the following relations on the set 1, 2, 3, 4, right? And then all I'm looking for is that for it to be reflexive, I need to be able to see that A is related to itself. I need to see that 2 is related to itself. I need to see that 3 is related to itself. And lastly, I need to see that 4 is related to itself. That is it about reflexive. So can you look through and tell me any of the relations R1, R2, all the way to R6, whereby the members of the set 1, 2, 3, 4 are related to itself? In other words, which of the relations R1, R2, all the way to R6 can be classified as a reflexive property?
Okay.
So R1
Hello.
to each.
R1.
Okay, so someone is mentioning R1. Let's check R1.
Yes. Yes. We have R1.
So let's
No.
start with the R1. So for R1, this is what we're going to have. We're going to check whether 1 is related to itself. When we are done, we check whether 2 is related to itself. We check 3 is related to itself and 4 is related to itself. We don't care about the others. So there's 1 related to itself. That's okay. 2 is related to itself. That's okay. But I don't see 3 related to itself. But I see 4 is related to itself. So because I'm not seeing 3 is related to itself, I'm concluding that it is matrix.
So R3.
R3.
That should be R5.
So before that, let's check R2. R2, 1 is related to itself. R2 is not related to itself. So this one
Yes, sir.
cannot be reflexive. This one too cannot be reflexive. So now let's come to R3. R3, 1 is related to itself. 2 is related to itself.
3 is related.
3 is
R3.
related. 4 is related. So R3 is said
4
to
is
be.
related to
Yes.
reflexive.
Now when it comes to R4, R4 is not.
No, sir, it's not.
So R4 is out.
Yeah.
Yes.
What about R5? Let's-
R5,
R5 is reflex.
okay.
2, 3, 3, 4, 4.
Okay. So R5 is reflexive.
Reflexive.
What about R6? Nah.
No, it's not qualified.
We have R3 and R5. Who can tell me what R4 is? Irreflexive. Very good. Yes, alpha is irreflexive. Very good. Because we don't have any of the elements related to itself there. Okay.
Then R6.
R6, yes, R6 too can be a form of irreflexive.
Yes.
Okay. So in other words, but remember, we cannot say R2 is irreflexive because 1 is related
Okay.
to itself.
Okay. So you
So
can
one-
say it's irreflexive when there's none of the
Related-
members related to itself.
Yes.
Okay. Thank you.
You're welcome. So we can move on. Okay. Now let's look at this example too. So for this example, we consider these relations on the set of integers, right? Remember that the numbers A, B are belonging to the set of integers that can be positive and negative whole numbers.
Okay.
So can we also look at it and tell me those which are reflexive? So I'll give you like 2 minutes to look. So please look at it 2 minutes and then let's discuss it after 2 minutes. So identify those which are reflexive and those which are irreflexive.
What is that?
Okay, so we can continue. I see some hands up. The one with iPhone. What's your name? You have iPhone as your Zoom name. Normally, it's best you change it to your name, okay? So I'll skip you to Emmanuel. Emmanuel, please, I see your hand up.
So can we say R4?
R4, right? Okay.
Yes.
We're going to look at it quickly. Charles.
R1 and R4.
R1 and R4. Okay.
Yes,
All right.
please.
Lastly, iPhone. You want to make a contribution?
Sir, please.
Okay.
R4.
You're also thinking of R4, right?
Yes. Yeah. I don't know how to change the name.
Alright.
That's why I'm a bit. Sorry.
Oh, you cannot change the name. What's your name?
I'm Asante.
Asante.
Yeah.
All right. So I've done it for you. Okay.
Okay, thank you.
I think I saw one bright hand up. All right, so let's look at it together. So we want to find out which of the relations is reflexive. In other words, which of them is related to itself. So if I pick one, I should be able to see one. If I pick two, two should be related to itself. Three should be related to itself. Zero should be related to itself. Negative one should be related to negative one. Negative two, same, all the way to negative infinity. So the first one, you can see that I'm having the set A, B is related to B, given that A is equal to or less than B. And that's what it means. So once I have A equal to B or less than B, I'm good to go. Why? Because anytime I pick A can be any number at all, 0, 1, 2, 3 to positive infinity, or A can be negative 1, negative 2, negative 3 to negative infinity. Then B can also take the same value. Or the A value might be less than the B value. So because I'm seeing equality there, I can easily conclude that R1 is reflexive. Now, when I come to R2, for any possible value of A, it will always be strictly greater than the value of B. So they will never be equal. So there's no way R2 can be reflexive. Rather, R2 can be irreflexive because there's no way A and B will one way or the other relate to each other. So R2 is a straight up irreflexive. R3 is also straightforward. I can see A equals to B or A equals to minus B. So at this situation, because there's A equals to B, here, R3, I don't need a switch here to let me know that it is also reflexive. And the FRC has to do with the A equals to B. Now when I come to R4, you don't have to think about it because for whatever value of A, the same value of B. So R4 is also reflexive. Now we look at R5. What R5 is saying is that if I pick any B value and I add 1 to it, I should get an A value. Wow. What it means is that A and B will never be the same. There's no way A and B will ever be the same. Hence, R5 will never be reflexive. Let's look at R6 critically. So for R6, I'm saying that A plus B is less than or equal to 3. Now, here, if you check very well, if you pick any A value and a B value, let's say A is 0, B is also 0, right? 0 plus 0 will give you a value less than 3. That's okay. We can pick negative values, right? A is -1, B is -1. That should also give you a -2, which will always be less than what? A 3. If I go to -5, I'm still going to have -10. So all negative numbers, if they are the same, will always give you a value less than 3. Now, when I come to positive values, I'm looking at 1, A is 1, B is 1. So I'm going to have 1 plus 1. That'll give me what? 2. When I go to A is 2, and then B is 2, I violate the rule because 2 plus 2 give me 4. And the 4 is nowhere lesser than 3. So at this situation, I can never say that R6 is reflexive. Because I wasn't given restriction. If I was given restriction to do with only negative integers, then I'm good to go. But this one, there's no restriction. So I need to be able to understand the fact that A can be 2, B can be 2, A can be 3, B can be 3, A can be 4, B can be 4, all the way to positive infinity. Okay, so we're good.
Yeah,
So in
so
this
question.
case, we can say reflexive. R2 is reflexive. R5 is also irreflexive. And then probably R6 cannot be reflexive because there's instances whereby A is 0, B is 0. So that don't work. Yes, please go ahead with your question.
So with a relation being positive and negative, does it mean that both integers can be negative at the same time, also positive?
Like the example R6, right?
I mean, like the R3.
So
Yeah,
R3, that's why you
we
can
have
see all there.
we have A being equal to B and A also being equal to negative B. In this case, that means both of the integers there are negative and positive.
Yes. So in this case, you're right. So I can have A to be A and B to be 2, 2, right? And then
Okay.
an instance here, I can also have 2, negative 2. Okay,
Oh,
but I
okay.
don't change anything because if you come here, right? If you check, let's say for example, if I check out R5, I can see my 1, 1 here, I can see my 2, 2, I can see my 3, 3, I can see my 4, 4, and I can see different pair combinations. Can you see? Which is not part of the relevancy we are looking at here.
Okay.
So we don't have an issue with having 2, negative 2, and then 2, 2.
Okay. Thank you.
You're welcome. So let's look at symmetric. So for symmetric, A will not be related to itself, but A will be related to B, provided B is related to A. So see it in this way, you are related to those of you in a relationship, the girlfriend-boyfriend relationship, for example. So you have A being maybe the lady, and then B being the gentleman, right? So A is related to B. The love that A is having for B, we expect the same love to be in return. So for symmetric, once A is related to B, B has related to A. The same love. No two ways about that. You cannot love someone and the person doesn't love you. It exists, but when it comes to symmetric, it doesn't exist. For symmetric, once I love you, also love me back. And that's why we are saying that a relation R on the set A is called symmetric if for B related to A, there's always the case that A will always be related to B, no matter what. So once A is related to B, B has to be related to A. That means an element is related to a second element if and only if the second element is also related to the first element. That's it. Okay. Now, if an element is related to a second element, but the second element is not related to the first element, then the relation is said to be not symmetric. So once A is related to B and B is not related to A, then we can say that that particular relation is not symmetric. For it to be symmetric, when A is related to B, B has to be also related to A. Okay, so this is also straightforward. So we can have this example, the relation consisting of the pairs XY, where X and Y are students at the same at your school with at least one common class, probably can be symmetric. Okay. So all the students who are probably in this class, we are assuming that in terms of the course we are doing, we are all related. So that's fine. Now, another relation can also be a relation consisting of the pairs XY, where X and Y are students at your school. X probably will have a higher grade point average than Y, it's not symmetric. So if at the end of the semester, if you see your GPU, and then probably we have someone who is having a GPU of 3.9 and another person having a GPU of 2.1, then those two are not related in terms of symmetric property. So for symmetric, they should all be around the same level. The same love is given. If I give you, they should also give the same love. Now let's look at some example of the symmetric property. So for the symmetric property, we have the same example, R1, R2, R3, all the way to the R6. And based on this, we want to say which of these relations can be symmetric. Can you try your hands on it? So tell me which of them is symmetric. 2 minutes. Okay, so can we look at it together? So let's see. For it to be symmetric, if I come across 1, 2, 1 is related to 2, I should see 2 is related to 1. That's the meaning. So once I have 1 is related to 2, I am okay. I should also see 2 is related to 1. See, so these guys are okay. Then when I see 3 is related to 4, I should see 4 is related to 3. I'm not seeing that. Hence, this cannot be symmetric. Can you see? This is all wrong. Not be symmetric. Now, when I come here, 1 is related to 2. Of course, 2 should be related to 1. So this is okay. So this can be symmetric. Now let's come to R3. R3, I see 1 is related to 2, which is okay. I have to see 2 related to 1. That's it here. If I see 1 is related to 4, I should see 4 is related to 1. Yes, that's it. So I'm good. So this one, for the rest, 1 is related to 1, 2 is related to 2, 3 is related to 3, 4 is related. That I don't have an issue, because if A is 1, B is 1, right? I can say that A is related to B, B is also related to A. So for this reflexive property, it will always be symmetric. If someone is related to itself, right? He himself is the A, he himself again is the B. So that property will hold. Okay. At this situation, our main thing is the opposite ones. 1 is related to 2, there's 2 is related to 1. 1 is related to 4, there's 4 is related to 1. That's good. So at the end, this guy too is also symmetric. Now, when I come here, I see 2 is related to 1. I should see 1 is related to 2. I don't see that. So at the end, this is not symmetric. Now I come to R5. 1 is related to 2, which is okay. Only 2 is related to 1. I cannot see 2 is related to 1. So of course, this guy is not symmetric. Then of course, when I come here, 3 is related to 4. I don't see 4 is related to 3. So this is also not symmetric. So for the symmetric ones, I only have R2 and then R3. These are the symmetric ones. Okay. Quickly, let's look at anti-symmetric. Then probably.
Hello, sir. Hello, sir.
Then I can. Yes.
So can I say, with considering the symmetric property, you have to ignore. Okay, you have to ignore because the reflexive property is always symmetric. You have to ignore that and look at the next one after that one. Whenever there is a reflexive property in it.
That's it.
Again.
For the reflective, it will cut across all.
Yes.
You can use it for symmetric. If I only go to the next property, which I'll look at next week because of time, transitive property, you realize that the reflexive property 1, 1, 2, 2 will also be there. Okay. So in this case, as we said, you ignore all the reflexive ones and look at the once there is a is related to B, there should be a B is related to A. Once you're able to achieve that across, then you can say it's reflexive. Sorry, symmetric.
Okay, sir. Hello, sir.
Yes.
So in this case, I don't have to get all the combinations within the set of numbers given. Badly, even if I get one, it holds, right? Meaning it's symmetric. Just
if you
like
get one of those, like for R2.
Okay, so in the first example, R1, we have 1, 1, 2, and 2, 1. But then
But then there is 3 and 4, and there's 4 and 1.
Yes. Okay, so let's use R2 set. So R2 we have 1, 1, 1, 2, 2, 1. So with that one, the set of numbers here only comprise of just 1 and 2 from the main set, and 3 and 4 their combinations are not there, but it holds.
Yes, so it holds. Because R2 is a complete division. Although there is nothing about 3 and 4 inside, it's still correct.
Okay, so please, can you switch to the reflexive one so that I'll just.
You mean I should go back to the reflexive one, right?
Yes, sir.
This one or the previous one?
The previous one, sir.
Okay.
Okay, so here, what happened is, whenever we see a combination of like 1, 1, we need 2, 2, 2, we need 3, 3, and 4, 4 for it to hold as a reflexive property.
Yes.
So, but with a symmetric, even if there is one that are occurring with those two combinations, like 1, 1, 2, 2, they still hold.
Yes, that will hold.
Okay, so you don't need a combination of all the sets in the main set.
No, you don't need all of them there.
Okay, sure.
Make it work. Okay. But for the reflexive, all should be there.
Okay, sir. Thank you.
So let's look at the anti-symmetric. So the same way we have the irreflexive property, whereby we shouldn't have a particular element related to itself. For the anti-symmetric, if A is related to B, we shouldn't see B is related to A. That's it. So we say that a relation R on the set A such that for all A, B belonging to A, if A is related to B, then B is not related to A. It's called antisymmetric. So it is called antisymmetric when A is related to B. I see 2, 1, but I don't see 1, 2. I see 3, 1, but I don't see 1. Okay. Now that means that a relation is antisymmetric if and only if there are no pairs of distinct elements A and B such that A is related to B, but B is also related to A. So in this situation, what we are trying to say is that if A is related to B, B shouldn't be related to A. But note that the terms symmetric and antisymmetric are not opposites, right? Because a relation can have both of these properties or may lack both of them. That's a key thing we need to understand here. And how do we do that? If a relation should have both of the properties, then if I have a relation 1, 1, right? 3, 3, 4, 4, it can exhibit both symmetric and antisymmetric. Why? Because if I have 1, 1, 1, 1 in antisymmetric can mean only AB. 2 2 can also mean AB. 3 3 can also mean AB. 4 4 can also mean AB. But for it to exhibit symmetric, once I have 1 1, which is AB, I should have another repeated 1 1, which is also what BA. And I know you said if a particular pair is repeated 2 times in the same pair, and that is why we can say that the reflexive property can hold for both symmetric and anti-symmetric. So in this case, a relation can have those properties. There are instances to implement. So let's look at this example. For it to be anti-symmetric, we're saying that, for example, if I have 1 2, I shouldn't have a 2 1, right? So this one has a 1 2 and 2 1. So hence this guy cannot be. Now out 2 2 1 2 2 1. This one too is out. When I come to out 3, I have a 1 2, right? I shouldn't see a 2 1. I see a 2 1 here. So this one cannot be anti-symmetric. Let's come to out 4. Out 4, I have a 3 1. I shouldn't have a 1 3. Yes, that's good. I have a 3 2. I shouldn't have a 2 3. I have a 4 1. I shouldn't have a 1 4. That's good. I have a 4 2. I shouldn't have a 2 4. That's good. I have a 4 3. I shouldn't have a 3 4. So R4 can be anti-symmetric. Okay. When I come to R5, 1 2 shouldn't have a 2 1. Okay. 1 3 shouldn't have a 3 1. 1 4, I shouldn't have a 4 1. 2 3, I shouldn't have a 3 2. 2 4, I shouldn't have a 4 2. If I 3 4, I shouldn't have a 4 3. So if that is the case, then this guy can also be what anti-symmetric. And of course, there's a 3 4, there's no 4 3. So at the end, I can have my R4, R5, and R6. And these are all anti-symmetric. Then I can now your parts for you to try your hands on at home and before I meet you next week, right? Is that write relation R on the set 1, 2, 3, 4, such that R is both symmetric as well as anti-symmetric. R is neither symmetric nor anti-symmetric. So you can take a picture of this. Okay, and then try your hands on it. Is there any question for me? Is there any question?
Sir, please, will you post the slide?
Yes, I'll share the slide. Okay, so if there's no question, then I think I'll leave you to go for your next class.
You said you wanted to talk to us about the IA or something. After class.
Okay, so when I meet you next week, I'm doing the exams 29th of April. So when I meet you guys next week, maybe I'll let you have the IE next 2 weeks, hopefully. Okay, so I'll try my best to finish what I have to teach you next week when I'm done.
Sir,
Yes.
please could you explain how the R can be both symmetric and is anti-symmetric? I don't really get it.
That's your sign. You okay? That's your sign. Look at it. Okay. Okay, someone has asked what about tutorials. I'll get, please get in touch with my TA, like Benson or Evans. We need to have some online tutorial classes with you guys. Okay, so
Okay.
maybe next one, and then am I right? Yes, Docas. Yeah, can you get in touch with my TA? Right.
All right, sir.
All right. So let me leave you, and then we keep in touch. I'll see you next week.
So please the slide.
I'll upload it.
Okay. Thank you.